Let's again imagine a thin sheet of metal where I know the density and I'd like to find the mass. We'll keep the metal sheet itself simple. We'll make it a rectangle. Say of base 2 centimeters and height 1 centimeter. And let's pretend somehow we know the density of this as a function, not just of x, but also of y, when I impose a coordinate system in the following way, about like this. Let's make that the x-axis, this the y-axis. X goes from 1 to 3, y goes from 1 to 2, and based on that coordinate system, somehow I know the density as a function of both x and y, a multivariable function, is 2x plus y. This is a function of two independent variables. Both x and y are independent variables. What's the dependent variable? I haven't given it a name. The most common thing to do is to call it z. Z equals delta of xy, but I think I won't bother. We'll just use function notation like this, where delta is the name of the function. This is a thin sheet of metal, effectively a two-dimensional object. The mass is going to be, density is going to be mass per unit area, say grams per square centimeter. And I'd like to know what's the total mass. I made this example simple enough that we actually could guess the answer ahead of time without doing any calculus. This density function increases in value, look at its formula, as both x and y increase. In other words, in this xy plane, as I move upward and to the right, it's going to increase in value. So its smallest value will be at the lower left corner of the sheet of metal, right there. What's its value there? It would be delta of 1, 1. To figure out what that is with this multivariable formula, you just replace x with 1 and y with 1. It's pretty simple. 2 times 1 plus 1 is 3. This would be 3 grams per square centimeter as the density at that point, meaning, never forget what that means, if you took a small chunk near that point, if it was sufficiently small, you multiply 3 times the area of the small chunk, it would give you the approximate mass of the small chunk. Grams per square centimeter times a small area in square centimeters would give you a small mass in grams. At the other extreme, up here, upper right corner, delta of 3, 2, x is 3, y is 2, plug into the formula, you get 2 times 3 is 6, plus 2 is 8, 8 grams per square centimeter. So for a small chunk of area near that point, the mass would be 8 times the area, whatever that small area was. It's a linear function as well in both x and y. You would think, because of that, its average value over the entire rectangle should be the average of these two numbers. 3 plus 8 is 11, divided by 2 is 5.5. That should be the average value of this function over the entire rectangle, because it's such a simple function, a linear function. If it were more complicated, like 2x squared plus cosine of y, then all bets are off. It would not necessarily be the average of the extremes, but because it's so simple, it should be the average of the extremes. And in fact, if you evaluate it at the midpoint of this rectangle, x is 2, y is 1.5. Into this formula, you would get 4 plus 1.5 is 5.5. Yeah, 5.5 is the average of 8 and 3 grams per square centimeter. So the average density is 5.5 grams per square centimeter, it seems. So we would predict an answer of 5.5 grams per square centimeter, the average density, times the area of the entire rectangle. Base times height is 2. square centimeters. The square centimeters cancel, giving us 11 grams. That's our prediction. To truly know whether it's right or not, we need to do calculus. And again, doing this kind of prediction would be less certain if this function were more complicated, if it were a nonlinear function. We'd only be ballparking it in that case. So how do you use this calculus for this? We did vertical slices if the density function depended on x, because then along a vertical slice, x is approximately constant. And we did horizontal slices when the density function depends on y, because along thin horizontal slices, y is approximately constant. This depends on both x and y. I can't do thin vertical slices or thin horizontal slices, but maybe I can do both. Yeah, do a thin vertical slice. Okay, I'm picking the midpoint there, but I didn't have to. And a thin horizontal slice of small width delta x there and small height delta y there near some point xy. I happen to center this at the midpoint. I didn't have to do that. The area over a small rectangle near that point would be approximately constant because x and y are both approximately constant. What is the small mass of that small rectangle? What's delta m? Assuming delta of xy, this function, is approximately constant, I just do a product. Approximately delta of xy times the area. This would be in grams per square centimeter. This would be in square centimeters. Square centimeters would cancel, giving you grams. That's the mass of the small chunk. Let me write down the infinitesimal version of this too. I'll put it in parentheses here, or dm equals delta of xy dA would be the infinitesimal version of that. What's delta A though? It's a rectangle. It's delta x times delta y. Go down here, delta m. It's then going to be approximately delta of xy, that function times capital delta x times capital delta y. In an infinitesimal version, dm would be delta of xy dx dy. You're going to add things like this up to get an approximation for the entire integral, for the entire mass. The total mass is going to be the sum of the little masses, which is going to be approximately a sum that looks like this. Infinitesimally, we could write the total mass is the sum like this. An integral, where you imagine the integral to be a sum, even though it's technically not. But how do we actually do this integral? What have we done before this point? We've always looked at these Riemann sum things and let delta x or delta y go to 0. But I've got a delta x and a delta y. Do I let them both go to 0? Yes. Let delta x go to 0 and delta y go to 0. Now that's a, you might call a double limit. And double limits are technically kind of subtle. I mean, do you let delta x go to 0 first and then let delta y go to 0? Or do you let delta y go to 0 first and then delta x? Or do you somehow let them both go to 0 at the same time? And do they go to 0 at the same rate? Does it matter? All those could be questions you might try to ask and try to answer, but it seems like it would be difficult to try to answer, at least. I mean, I asked them, but it seems like that might be difficult to try to answer. We don't worry about that. It's hand-wavy, non-rigorous math. Feels like magic, but don't worry about it. So what do we do? we do a double integral with, well, I wrote one integral sign in each of those spots, but traditionally you write two integral signs. We could write double integral of, okay, let's write it this way. Let me go back to using a dA here. Let me write delta of xy dA is sort of the more abstract way to write it. We could also emphasize that it's over this rectangle. We could give this rectangle a name. How about cursive R for rectangle? It's somewhat traditional to write it this way. A double integral of this mass density function, mass per unit area of a thin plate over the thin plate itself, the rectangle shape. But you look at that and say, hey, that's kind of abstract. How do I actually calculate it? What I'm about to write down is actually not a definition, but a theorem that you can calculate it as what's called an iterated integral. It's two integrals where one of the integrals is thought of as being an inner integral that you do first, and the other integral is thought of as being an outer integral that you do second. Now, I'm going to use parentheses to emphasize that, but you should realize that eventually we just get rid of the parentheses. We don't bother. I'm going to write an integral sign, then parenthesis, another integral sign, delta xy. Since I thought of dA as being dx dy, I will do it in that order with dx for the inner integral and dy for the outer integral. And we do need limits of integration. The inner integral, you can see, that's done first is with respect to x. I will treat the y as a constant. What are the limits of integration for x? Look at the picture. X goes from 1 to 3. Now, we will do the integral, but imagine doing it without actually doing it. You're doing this integral with respect to x. You're treating the y like a constant when you do the integral here. Only x is the variable. You'll let x go from 1 to 3. When you calculate it, the answer will still involve y. The y won't go away. The outer integral, though, is with respect to y, ultimately making the y go away and giving you a number in the end. Y goes from 1 to 2. Now, this is simpler than I could have made it. I could have made the sheet of metal be shaped like a triangle or semicircle or something like that. Then the limits of integration get more complicated. In fact, the inner integral, if we, for example, had a triangle, the limits of integration would not be constants. They'd be things that depend on y, actually. Weird, but true. They could depend on y. Could I do it the other way around? Could I do the inner integral with respect to y and the outer one with respect to x? Yes, but that again is a theorem. It's called Fubini's theorem, if you want a name. That says you can do it either order. There are certain conditions on delta that must hold. Continuity is good enough. But anyway, let's now go ahead and do the integral. Keeping parentheses, the delta function is 2x plus y. I'm integrating first with respect to x, treating the y as a constant. Keep using parentheses. Integrate 2x, I get x squared. Integrate y does not give me 1/2 y squared because I'm treating the y like a constant. Pretend it's 10. If that y were a 10, integrate with respect to x, I get 10x. In general, I get y times x. X goes from 1 to 3. Continue treating the y like a constant. If I plug in x equals 3, I'll get 9 plus 3y. Subtract what you get when you plug in x equals 1, 1 plus y. This function simplifies to 8 plus 2y. And now that's an ordinary calculus 1 integral with respect to y. Yes, thank you. I made the exact same mistake in the first sections class. It must have been completely subconscious that I made the same mistake again. So do that integral. What am I going to get? 8y plus y squared. Y goes from 1 to 2. We better get 11.5 here, right? Or no, 11. 11 is supposed to be the answer. I plug in 2, I get 16 plus 4. Subtract what I get when I plug in 1, which is 8 plus 1. 20 minus 9. There we go, 11 grams, just like we predicted. Fun, fun, fun. Happy that we got what we predicted. If, again, that function were more complicated, nonlinear, I'd have to like somehow guess the average value if I'm going to estimate the value of the mass. That can be tough for a nonlinear function. It can be helpful to make a certain kind of graph that I'm not going to show you now to help you guess the average value. But it would be a guess. Technically, the average value is defined to be the value of the integral divided by the area of the region. Here we guess the average value and we multiplied by the area of the region to find our guess for the integral. And it was right. It turned out exactly right.